Welcome back. Now I'm pleased to hear that a few of you are building your own PlasMa machines. There's a link in the description to one of these, so I thought it might be useful to revisit the programming development route from start to finish by way of walking through an example program. Now this may be heavy going if you're just starting out. It's going to span a few videos and it's mainly about PleX, and there are no flashing lights till the end. You have been warned. I want to walk through the complete source code so you can either copy it or rewrite it in your own way and then run it on the PlasMaSim simulator, or if your machine is powered up and waiting for input, the real McCoy. Now assembling your program by hand and entering it using the front panel switches hasn't changed much since the prototype, and the toy instruction sets have remained fairly static, so you can certainly get stuck in with toy programs straight away on your new machine. But there have been a few additions to the PleX instruction set and also the PlasM assembler, which are applicable to all emulations, so I'll be discussing these as well. The example program was to test some floating point functions, so there are a lot of system calls, but it's much simpler than the lunar lander demo in the previous video. This one just draws a simple graph on the oper and is small enough to copy the source code direct from the screen. The graph is a single cycle of a trig function, where one axis is the number of degrees and the other axis is the sine or cosine of that number. Now, unfortunately, the oper screen is, as its name implies, designed to be an operator's console, as used on some old-school mainframe computers. So there are no high-resolution or high-speed graphics we now take for granted. So unless we use an external device, we'll have to make do with simple character-based blobs to make some semblance of a graph. Now, a later video will show a more typical use for the oper screen from that era. This oper has more columns than lines, so I've decided to rotate the graph so the vertical axis represents degrees. I'll use steps of 20 degrees for each line, so the 18 possible lines will represent 0, 20, 40, 60 and so on. And if you do the sums, the last line will be 340 and not 360, but this is okay as sine or cosine 360 is the same as sine or cosine of 0. So how about the horizontal axis? Well, there are 36 columns, and we'll use 3 of these to display the degrees value, and that leaves 33 for the graph. Definitely not high res. And the result will need scaling to fit into this space, and if you're unsure of the range of values to expect, you can use a calculator with trig functions to experiment, or better still, write a floating point calculator program for PlasMa. You may remember these earlier calculator demos. They only worked with integers, so there's another challenge for the to-do list. Now here's an overview from the printout I made earlier. This bottom level routine, display line, does most of the work and displays one line at a time on the oper. Each line starts with a degrees value and then the result in the form of a blob at the correct point along the line. Now the routine is called by this one, plot, which handles the degrees variable. First initializing it, then incrementing for each line till it reaches the maximum. And finally the top level routine, which handles the keypad buttons for you to choose which type of plot you want, sine or cosine. Now it may not be the most efficient way of doing it, but feel free to experiment. Now the rest of this video will be a walkthrough of the code, so if you're not interested, skip to the next one. I'll use the printout for this, but we'll display a clearer version later, so there's no panic now if you want to copy it. The %s directive, as always, must be present. It defines the source code language, so the assembler knows how to process the file. 3 means PleX. Now these equate definitions are copied from an include file I've mentioned before, which contains all the system calls, or extra codes, in PleX. Now rather than list the whole include file, I've extracted the subset used in this program. So what you see is all you need. And as explained before, these are my own conventions for names and usage. You can use whatever suits you, and at the end of the day, the only things which matter are these binary values. Right, first a few comments to remind me which registers I'm using for global values, and then more equates specific to this program as opposed to the previous ones which normally live in an include file for sharing with other programs. Here's the start of the program code. As I'm sure you'll know by now, a $ prefix means hex, and PleX RAM starts at address 16, which is hex 10. Now these comments below should tie in with the overview if you want to refer back. First, the oper screen is cleared and the help message or user instructions are displayed. This routine wait oper has been covered before. Peripherals operate asynchronously to the CPU, so if you forget to wait, you'll find they either won't work or won't work consistently. And most of the programs I've shown up to now have all just waited in a loop if the peripheral is busy. Now, this is an inefficient use of processing power, but it's okay here, and there's more on this in a later video. The help message is displayed by loading the start address of the text into register D, then using a system call to display it. Now here's the text string. I use an S prefix to remind me it's a string, and it just says which keypad buttons do what. Now embedding text in quotes is a relatively new assembler feature. You don't have to use them, but I think it's clearer, and it also allows more scope with the text contents, such as non-alphanumeric characters or leading and trailing spaces, which would be ignored if quotes were not used. Right, this is the start of the outer loop. The first statement flushes the keypad. Now, this is optional, but if you don't do it and press a button while it's plotting, the code will act on it next time round without waiting. This is because the keypad device has a single character buffer, which can be useful sometimes for type ahead, but in this case I wanted the program to always wait at this point. Register 0 is used for this button value, which is going to be ignored, but I always OR in the register number as per the convention, even if it's 0, as I think it clarifies the code, and it's also easy to use a different register later. Right, this is where the outer loop waits for a button press, so we do need to check the status here. The wait button routine is just like wait oper, but this time it loops until a button is pressed. We can now read the keypad's device buffer to see which of the 16 buttons was pressed, and the system call attribute is set to A, so the button value 0 to 15 will end up in register A. This is then compared to the constant equate values for buttons A and B, which are up here, and if neither was pressed, it loops back and waits for another button. Otherwise it starts to plot. Right, before moving on, a new assembler feature: label names no longer have to be unique. I don't know about you, but I was finding it harder and harder to find short names which were unique, especially with large programs. It's a simple solution, but works like this. Labels can still be defined with a dot prefix as before, but you can now define them with a colon prefix. And if you do this, you start a new scope or range for subsequent labels. There's only one scope in effect at any one time, and each colon label redefines it, or you can clear the scope altogether with a colon statement. And whenever you use or reference a label, the assembler looks for a matching label within the current scope. So down here we have two more labels, sign and cos. Now these won't clash because they're under the display line scope. Now if you really do want to reference a label outside the current scope, you prefix a label with the required scope name and a dot. So say you wanted to jump to this sign label down here, it comes under the display line scope, so you'd write jump display line dot sign. Now you can use scopes how you like. My convention is to use scope labels for every subroutine entry point. You may have spotted them already. There's this one here, and wait button, wait oper, even though these don't have any local labels within the routine. And finally, clear the scope right at the end for the data labels. Okay, back to the plot. Sorry about that. First, we clear the instructions from the screen and then initialize the degrees value. Now this is held as a floating point number in register pair 2 and 3. So this system call clear floating point initializes it to 0.0. And as normal, the register pair is ored into the function word. And if you're wondering why it's just 2 with no mention of register 3, the second number for a floating point pair is implied, so is not needed. Now you could use the accumulator instead, but this is how I've done it. The register pairs were covered in detail in video 27. It now loops, displaying lines one at a time, each time incrementing the degrees value. The increment amount is defined as an equate and is loaded into the accumulator, so this system call add floating point adds it to the current value in register pair 2 and 3. Here's degrees inc, and this is the maximum value, which is used here the same way. Load it to the accumulator and compare it. Now just a point about system call function words with multiple attributes, like these. Most of them use the same ordering convention as the opcodes. Here's an opcode, move, rd is the destination, and shelp is the source. Here's a system call, 2 is the destination, and f is the source. Now this 2 refers to register pair 2 and 3, and this f refers to the accumulator, which brings me to another convention. If the attribute is f, as opposed to a register number, it refers to the accumulator instead. Remember that PleX does not have a register f, unlike the toy emulations. Okay, this saves having extra system calls just to handle the accumulator, but note that not all system calls do this. Some treat f as illegal, and others treat it as an extra control function. We'll see one later on. If in doubt, refer to the instruction set manual. The routine then either returns if finished, or displays a new line and loops back to the next line. Okay, on to the display line routine. The current degrees value needs to be converted to 3 ASCII characters and then displayed. And the conversion is done with this system call here. Convert floating point to ASCII string. And this may look a bit daunting with 3 attributes, but saves a lot of programming effort. The first attribute is a register number which holds the conversion mode, which is a set of bits defining options such as decimal, hex, or left-right alignment, and so on, and also the field width to be used for the result. The register C is used for this, so it's loaded with a predefined value, which is here. The default bits of 0 is okay in this case, so all we need is the field width, which is defined here. And this is an example of an equate referring to another equate, which is perfectly okay. The second attribute is the start address of the ASCII string to hold the result, and I'm using register D for this. There's register D, and this S degrees is the destination string. The string is allocated space in RAM using the fill directive, and the expression calculates the fill amount, which is in words. The final attribute refers to the actual floating point number to be converted, in this case register pair 2 and 3, so we need a 2 here. Again, the order is destination first, then the source. When the call is returned, the ASCII characters representing the number of degrees will be in the string array in memory, and we just need to display this. And this is done exactly the same way as with the help message. Register D still holds the start address of the string, so it can be ored in here. The next part calculates the sine or cosine value and works out the horizontal position for the blob. But the trig functions work with radians, not degrees, so the value needs converting first. Now, to avoid trampling over the current value, register pair 2 and 3 are first copied to another pair, 4 and 5, using this system call. Now, you could copy the pairs using standard opcodes. For example, move R4, R2, and move R5 with R3. Now, that may be quicker than the system call, but there is a subtle difference in the way the flags are set. It makes no difference here, but check the manual if you use this method in your programs. The conversion factor, degrees to radians, is defined as an equate up here. And an expression is used to clarify how it's derived. But the assembler is doing all the work here, so there's no memory or time penalty in the final machine code. The factor is loaded into the accumulator and multiplied with the register pair 4 and 5. Again, source to destination. So register 4 and 5 is overwritten with the result, which is why we needed the copy. Now to calculate the trig result. Register A still holds the keypad button from the start, so this can be checked here to pick the required function, sine or cosine. The code jumps to the relevant system call, this one or this one, to calculate the result. The radians are in register pair 4 and 5, and the cosine will go into the accumulator. The final section converts the floating point result into an integer x coordinate for the oper screen. The result range is -1 to +1. There's no abs or absolute function, but we can just add 1, so the range becomes 0 to +2. Then divide by 2, so the range is now 0 to +1. And this can now be scaled to fit the required graph width. And finally, converted to an integer value in register 6. Looking at this calculation again, I've probably made a meal out of this, but that's hindsight for you. Maybe you can simplify it with your version. Now, as an aside, this system call converts a floating point to a signed integer. That's the S. Now, there isn't one for unsigned integers, but we've already ensured the number is positive. Right, nearly there. The oper X cursor position refers to the column, so we just need to add an offset to allow for the 3 characters of degree display, and then use a system call to set the position. Now, this call can set either X or Y, or both, and in this case the attribute value F means ignore that attribute, so only the X coordinate is set from register 6. And now it can display the blob at that position. Phew. Okay, that's the source code. Join me in the next exciting installment.